Welcome to the video lecture series for Texas A&M University Course Math 152. Today we will take a look at Section 8.4, Integration by Partial Fractions. You can find the accompanying handouts at bit.ly/Raelene Math 152. Let's begin. For warm-up, let's integrate the sum of two fractions. We can apply distribution of the integral, and we can get the integral of 1 over 2x minus 3 dx plus the integral of dx over x plus 4. And for the first integral, I will just apply a substitution, and I will let t equal to 2x minus 3, so that dt is equal to 2 times dx. And then we will get the integral of 1/2 times the integral of dt over t. Plus the integral for the other one won't change, so I'm actually going to integrate it straight away. And I can put a constant already, and when I finish integrating this and back substituting, I get 1/2 times the ln of 2x minus 3 in absolute values, plus the natural logarithm of x plus 4 in absolute values, and then plus c. In part B, add the two fractions. So the first thing we must do is get a common denominator. So the first fraction is missing the x plus 4. So we unreduce the first fraction by multiplying by x plus 4 over itself. In other words, we multiply by 1 in the form of something over itself. The second denominator is missing the 2x minus 3, and we unreduce that fraction by multiplying by 1 in the form of 2x minus 3 over itself. Then we get the common denominator of 2x minus 3 times x plus 4. And then we get x plus 4 plus 2x minus 3, and we have 3x plus 1 all over 2x minus 3 times x plus 4. Which is, in fact, if we expanded the denominator, I don't recommend that we usually do expand the denominator because we want to keep factored form as much as possible so we can look for common factors to reduce. But let's just see how this leads into part C. If we expand our denominator in part B, we get 2x squared plus 8x minus 3x is plus 5x, and then minus 12. And so in part C, if we wanted to try to integrate, we might think at first that we want to use a substitution, and we could let t equal to 2x squared plus 5x minus 12, and therefore dt is equal to 4x plus 5 all multiplied by dx. But this substitution is not going to be very helpful because we need to have a multiple of 3x plus 1 times dx, and we don't have that. Rather, we can recognize that part C has an integrand function which is equivalent to part B, which is actually the integral we worked out in part A. So in fact, the answer to part B is 1/2 the ln of 2x minus 3 plus the ln of x minus x plus 4 in absolute values for both powers, and then plus a constant. So when the method of substitution here didn't work, we had an alternative, which was to decompose the fraction into its partial fractions. And so this is the idea behind the integration technique of this lecture. Just as some more review for the algebra, a quadratic expression ax squared plus bx plus c has non-real zeros if the discriminant is less than 0. And the discriminant comes from the quadratic formula. It's underneath the square root sign. The discriminant is equal to b squared minus 4ac. Such a quadratic is called irreducible over the reals, or does not factor over the reals, meaning it has no real roots. Number 3, special products and factoring. A quadratic expression ax squared plus bx plus c factors over the rational numbers if the discriminant is a perfect square. The reason for that is when we look at the quadratic formula, for example, if we were to set this equal to 0 and then solve, we would get solutions that x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And if the quadratic discriminant were a perfect square, then the square root of the perfect square would be a whole number. And as a result, there would be no irrational components to the solutions for x, and x would be rational, which means a ratio of integers. That is, of course, assuming that the coefficients a, b, and c are rational numbers in the first place. Part B talks about the rational root theorems, and if we want to find a rational root a of a polynomial p of x, such that p of a is equal to 0, then we can divide and repeat until p, the polynomial, is a product of irreducible factors. So for an example, how we might begin to proceed, or how we would proceed factoring x cubed plus 3x squared minus 4, is to list the possible rational roots. Notice that when we had two factors here, 2x minus 3 and x plus 4, that it is the first term multiplied by the first term, which gives us the first coefficient, and the last term in each factor, which multiplies by the other last term to give us the overall last term. And so we are going to look at factors of the constant divided by the factors of the leading term as indications of what the numerator and denominators might be of the roots. So for example, if 2x minus 3 is a factor, then the root is, solving for x equals 3 over 2. And the 3 was a factor of the 12, and the 2 was a factor of the leading coefficient. So this is the basis for the rational root theorem. If we are going to have any rational roots, then the possible ones have to come from plus or minus the factors of the constant term divided by the factors of the leading coefficient. And so in this case, we see that the constant term is 4 and the leading coefficient is 1. So we would have plus or minus 4 over 1, 2 over 1, 1 over 1. And since the leading coefficient only has a factor of 1 and no other numbers, we don't have to repeat this. Let's say that the leading coefficient was 5, for example. We could have 4 over 1, 2 over 1, 1 over 1, or we could have 4 over 5, 2 over 5, or 1 over 5. But in the case of the leading coefficient of 1, we only have one possible denominator. So then we want to actually to identify an actual, not just a possible root. And so to do that, if we found a root, we could plug it into the polynomial and get 0. So we're going to test. Probably the easiest x-coordinate or root to test is x equal to positive 1. So if we test x equal to positive 1, we will find that p of 1 is equal to 1 cubed plus 3 times 1 squared minus 4, which is 1 plus 3 minus 4, which is 0. And therefore, x equal to 1 is actually a root. It's not just a possible root of the polynomial. And as a result, x minus 1 equal to 0, so x minus 1 is a factor of p. What we want to do now is to perform long or synthetic division, if it applies, and fully factor the cubic polynomial. So we are going to do long division would be set up like this. And we had x cubed plus 3x squared minus 4. Don't forget the placeholder term of 0x. And so you could perform the long division, or in this case, the synthetic division will work. And if you need to review, you can see the Math 150 videos, section 2.3 on division. So we are going to take out the root of 1 and the coefficients of 1, 3, 0, negative 4, and perform the synthetic division. And we note that we get a 0 here for the remainder. This 0 is the same as p of 1 equal to 0. So that 0 is the remainder. And this tells us that our coefficients are going to be 4 plus 4x plus 1x squared. So far we have a partial factorization of p of x. We know that p of x is equal to x minus 1 times x squared plus 4x plus 4. And from here, you could check the quadratic discriminant or simply try factoring it by trial and error, and we get a fully factorized polynomial. Some other factoring techniques we need to know are difference of squares. A squared minus b squared will factor as conjugates, and so if we wanted to factor x to the 8 minus 1, we'd have to see this as something squared minus something else squared. We know 1 goes into the last block, and we don't take the square root of 8 because the exponent law says to multiply these exponents. And so we would get x to the 4 minus 1 times x to the 4 plus 1. X to the 4 can continue factoring as x squared minus 1 times x squared plus 1. And then we have our third factor still. And we can actually continue factoring x squared as x minus 1 times x plus 1 times the remaining two factors. We can also factor as a sum of squares using the imaginary number I, which is equal to the square root of negative 1. And we do so by recognizing that I squared is equal to negative 1. So 25x to the 4 plus 1 is going to be 5x squared plus I times 5x squared minus I. And we won't try to factor any further, so because we have coefficients here of 1i and negative 1i. To factor as a sum or difference of cubes, we note that a cubed plus or minus b cubed has a binomial factor times a trinomial factor. The binomial factor is the cube root of the first term, the same sign as the middle, and the cube root of the second term. Then to generate the trinomial factor, you take the terms from the binomial factor, you square the first, you multiply the two terms together and change the sign. There is no doubling involved here. And then you take the second term of the first factor and you square it. So applying that to 8x to the 6 minus 27y to the 9, I'm first going to write my difference of cubes very clearly. I know that 2 cubed is 8, and I know that 3 cubed is 27. But again, if I want to take the cube root of x to the 6, that really means x to the exponent of 6 over 3, which is x to the 2. And so inside the first bracket, I have 2x squared. Similarly, the cube root of y to the 9 can be rewritten as y to the exponent of 9 divided by 3, which is going to be 9 to the exponent of 3. And you should just expand that, get rid of the brackets, to confirm that you have the right breakdown. So I take the cube root of the first, same sign as the middle, cube root of the second term. Then I take my first factors, I square the first, I multiply together and change the sign. So I get plus 6x squared y cubed, and then I square the last. I will always get a positive for my first and third terms of the trinomial. And we get plus 9y to the exponent 6. If you expand that out, you should confirm that you get the two terms, 8x to the 6 minus 27y to the 9. Another technique for factoring is substitution. Here we notice that we have only even powers of x, x to the 4 and x to the 2. So we can say that x to the 4 is x squared squared minus 5x squared minus 36. And as always, when we have a repeated factor or a repeated expression or an inner function, that is a good candidate for substitution. So if we let u equal to x squared, we get u squared minus 5u minus 36. And this will factor as u plus 4 times u minus 9. I think I'll put that up here. And then we can back substitute in terms of x. So x squared plus 4 times x squared minus 9, and we can continue to factor over the complex number system. So we have a sum of squares, x plus 2i times x minus 2i times x plus 3 times x minus 3. In number 4, the least common multiple of two or more numbers is the smallest or least number that, this is actually incorrect, that all numbers divide into. So I think I'll just cross the rest of this off and fill it in. That all numbers divide into. So for example, if I have 2, 4, and 5, the smallest number that all of these numbers will divide into is 20. So the least common multiple is 20. So if we were to skip count, or count by twos, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and then skip count with 4, if we were to write these down, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and then 4, 8, 12, 16, and 20, and then 5, 10, 15, 20. We can see that 10 is common to 2 of the individual numbers, but not to all 3. And the first number that is common to all 3 is 20. However, if we had multiplied all 3 numbers together, we would have gotten another number that is common, which is 40, because 2 times 5 is 10 times 4 is 40. However, 40, while it is a common multiple, it is not the least or lowest common multiple. So 20 is the only LCM for the numbers 2, 4, and 5. The lowest common denominator is actually the same thing as the least common multiple, but this time it is of 2 or more denominators. So it is the LCM of the denominators of 2 or more fractions that are being added or subtracted. So we're going to determine the least common multiple, or if these were denominators of 3 fractions, we could refer to it as the lowest common denominator. So in the first case, 2 squared and 2 to the 5th, or 2 to the 5 rather, has a least common multiple or lowest common denominator of 2 to the 5. The reason is each number will divide into this evenly, and 2 to the 5 is the smallest possible number that all 3 have in common. In part B, we have 72, 36, and 48. And what we're going to do is factor this into prime factors. 72 factors into 8 times 9, and 8 is 2 cubed, and 9 is 3 squared. 36 factors into 4 times 9, and 4 is 2 squared, and 9 is 3 squared. And 48 factors into 12 times 4, which is 16 times 3, and this gives us 2 to the exponent 4 times 3 to the exponent 1. From here, the lowest common multiple or lowest common denominator, well, I'm going to take inventory. I need at least 3 2s and 2 3s. And that way we can say that the 72 will divide evenly. In order for 36 to divide into, we have to have at least 2 factors of 2 and 2 factors of 3, which we do, so we don't need to introduce anything more. Currently, the LCM is 72, and our first number will divide into the LCM 1 time. The second number of 36 will divide into the LCM 2 times, because there is an extra factor of 2 apart from 36's own 2 factors. Then, in order for 48 to divide evenly, we need at least 1 3, which we have, and we need 4 2's. However, we only have 3 2's, so we need to introduce another 2, and then we can say that the 48 will divide in evenly. So the LCM is actually 2 to the 4 times 3 squared. In the next case, we have some polynomials, and so let's just factor each one of these. We have x cubed plus 8, which we'll factor as x plus 2 times x squared minus 2x plus 4. We have x cubed plus 3x squared minus 4, which we factored earlier as, I think I'll write it here, x cubed plus 3x squared minus 4, x minus 1 times x plus 2 all squared. And lastly, we have 4x plus 8. So don't forget probably the simplest and first step in factoring, which is looking for a common factor. And so now when we come to take inventory to get the lowest common multiple, or the LCD, lowest common denominator, I'm going to take everything from the first factor, from the first denominator or number. I notice here I have a quadratic expression, and if I work out the discriminant, I end up getting 4 minus 16, which is a negative number, and therefore my quadratic x squared minus 2x plus 4 does not factor over the reals, and we will not be factoring over the complex numbers or doing any integration or calculus involving complex numbers. So I know that this is an irreducible quadratic, and so my first factors are going to be x plus 2 times x squared minus 2x plus 4. Then, in order for the second term to divide into the lowest common multiple, I need a factor of x minus 1, which I do not have, so I introduce it by multiplication. And then I need two factors of x plus 2. I have one, so I need to introduce another one. And now the x cubed plus 3x squared minus 4 will divide evenly into the LCM. For my third term to divide into, then I need one x plus 2, which I have at least one of, and I need a 4. And so altogether, my LCM is going to be 4 times x minus 1 times x plus 2 all squared times x squared minus 2x plus 4. In number 7, we are going to add the three algebraic or rational expressions, the algebraic fractions. So the first thing we need to do is get common denominators, and before we can do that, so the real first thing is to factor fully. So we get x plus 3 times x minus 3, and feel free to pause the video, try it on your own, and compare with me. And so we need to take some inventory to come up with the lowest common denominator. I need everything from the first denominator. By everything, I mean all of the factors. I need another x plus 3. And now the first and second denominators divide in. I need an x plus 3, which I have, and I need an x minus 2, which I don't have. So now I'm going to write this as all over the LCD, since I have stated what the LCD is equal. I know the first denominator is missing the x minus 2 and an x plus 3. So I'm going to unreduce by multiplying top and bottom by x plus 3 times x minus 2 with the current 2x. So I will have 2x times x plus 3 times x minus 2. In the second denominator, the second denominator is missing x minus 3 and x minus 2. So I'm going to multiply top and bottom by those factors. And in the third denominator, we are missing x plus 3 and x minus 3, so I'm going to multiply the 4 by both of those. And I'll leave this at this point. It's just a bit of exercise of algebra to expand correctly, collect like terms, try to refactor, and if possible, to reduce. Make sure that there is no reducing going on if there are adding and subtracting between, because these are no longer factors. Factors are expressions joined by multiplication only. Okay, moving on to the next exercise, or the next warm-up. The division algorithm states that numerator over denominator is equal to quotient plus remainder over denominator. And the fraction is proper if the numerator is purely smaller than the denominator. If the numerator is the same size as the denominator or larger, we say that the fraction is improper. So we are going to convert 7 over 3 to proper form by saying 3 divides into 7. It goes in 2 times with a remainder of 1. The remainder is not 1/3, but we say 2 and 1/3, meaning remainder over denominator. And then to go backwards to improper fraction form, we simply get a common denominator. We recognize that the LCD is 7, and the 5 has a denominator of 1, which is missing a factor of 7. So we unreduce the first denominator by multiplying, or the first fraction, by multiplying by 1 in the form of 7 over 7. This gives us 5 times 7 plus 4 all over 7, which gives us 35 plus 4, or 39, all over 7. Now, a lot of people have memorized this as 7 times 5 plus 4, but the reason we do 7 times 5 plus 4 is because we're just getting a common denominator. Now, in section 8.4 of Math 152, we are talking about the integration of rational functions. The word ratio is inside the word rational. So a rational function is a function that is a ratio or a quotient of polynomials. And the polynomials can be, or rather the fraction, can be in either proper or improper fraction form. So if we have improper fraction form, the degree of the numerator is greater or the same as the degree of the denominator. Otherwise, we can rewrite in proper fraction form where the fraction part has a numerator and that degree is going to be less than the degree of the denominator. So we are going to convert the rational expression x cubed minus 7x plus 1 over 5x minus 2 to proper fraction form and then reverse the process for part B. So we are going to do long division. 5x minus 2 divided into x cubed plus 0x squared minus 7x plus 1. And I'll do this quickly, but you should be able to do it without checking with me. 5x divides into x cubed, 1/5 x squared times, because we're saying x cubed divided by 5x. And so we multiply back and we get x cubed minus 2/5 x squared. We subtract. If the first terms do not sum to 0, you've made a mistake. And then we get 0 plus 2/5 x squared, which is 2/5 x squared, minus 7x. Now we're saying 2/5 x squared divided by the leading term, 5x, which gives us 2 over 25x. And you will notice that I'm keeping everything in a column. I have my quadratic column, I have my cubic column, I have my linear column, and I'm lining everything up to keep it organized so I can find any mistakes if I have them. Then I multiply 2 over 25 times 5x is going to give me 2 over 5x squared minus 4 over 25x. We subtract, and then negative 7 plus 4 over 25. Notice I'm doing all of my scratch work off to the side. Getting a common denominator, I get negative 175 over 25 plus 4 over 25 gives me negative 171 over 25. And that's times x. Then bring down the plus 1, and now we are saying negative 171 over 25x divided by 5x. So instead of dividing by 5, I can multiply by 1/5, giving me negative 171 over 125, and I multiply back. And I get 171 doubled. We're going to get positive 342 over 125. We subtract, and 125 over 125 minus 342 is negative 117 over 125. And so that gives me a quotient, which is the quadratic above, plus a remainder of negative 117 over 125. And so I'm going to rewrite f of x from part A in proper fraction form as 1/5 x squared plus 2/25 x minus 171 over 125 plus a remainder which is negative, so minus 117 over 125 divided by the denominator of 5x minus 2. If you take a look at the TI Inspire and you go to the menu, and then you can go to number, and you can go to fraction tools and proper fraction. From here you can type in the function that we had, which was hard for me to see, x cubed minus 7x plus 1 x cubed minus 7x plus 1 divided by 5x minus 2, and we can confirm our denominator. I think I've made a subtraction mistake here. We get negative 217, not negative 117. And of course that's 2, 3 minus 1 is 2. Okay, so we can see on the graphing calculator how to get proper fraction form. So in part B, we're simply going to get a common denominator. We multiply 3x plus 1 times 2x minus 3. I think it's 3x plus 1 times 2x minus 3, and then minus 5, all divided by 2x minus 3. We can see, of course, we've got two terms in the numerator, and the denominator could have divided into them, giving us the proper fraction form we had to begin with. So here we get 6x squared minus 7x minus 3 minus 5 is minus 8, all over 2x minus 3. So we can actually use a function on the calculator to reverse the process of proper fraction, which, if we take a look in the menu and we go to the number and fraction tools, it looks like common denominator. So if we want to get a common denominator between, let's see, what did we start with? 3x plus 1 plus a negative, so minus 5 over 2x minus 3, we end up getting 6x squared minus 7x minus 8 all over 2x minus 3. Okay, now we're ready to do a little bit more calculus. In number 10 we have an improper fraction, and our goal or our process for dealing with integrals of improper fractions is always to put the fraction into proper form first. So this is the one we just did, and we can see that we're going to get the integral of 1/5 x squared plus 2 over 25x minus, I think it was 171 over 25 over 125. Yeah, 171 over 125. And then we had the fraction part of negative 171, sorry, a negative 217, I think I'll take it from here, negative 217 over 125 divided by 5x minus 2. And put all of that in big square brackets, dx. So the first integral is just a polynomial, which is going to be straightforward, and I won't bother integrating that. And then we get negative 217 over 125 times the integral of 1 over 5x minus 2 times dx. And here we can use a substitution. Let t equal to 5x minus 2. Therefore dt is going to equal 1/5 of dx, rather 5 times dx. I'm getting ahead of myself. And when we integrate this part, we will get negative 217 over 125 times 1/5, the natural logarithm of t, which is 5x minus 2 inside the absolute values. So you can check this on the TI Inspire using the indefinite integral template, and you can use it from the improper fraction form immediately. Let's try that. We get x cubed minus 7x plus 1. And I'm going to highlight all that and put it in the numerator of my improper fraction. And the denominator is 5x minus 2, integrating with respect to x. And so we can see there's the natural logarithm with another 5 multiplied by 125, and there is the integration of the quadratic polynomial. Of course, don't forget plus c. Okay, so that is our first technique when we are integrating a rational function with an improper fraction. We have to put the improper fraction into proper fraction form. Okay, so now we're really getting down to the process of decomposing a fraction that is already proper into its partial fraction pieces. From now on in the rest of the video, I won't complete any of the integrals. You can try them for yourself once we have decomposed the fractions, and you can check your answers on the TI Inspire. So the process of working backwards to break apart or decompose a fraction as the sum and or difference of its partial fractions is called partial fraction decomposition. The denominators will be linear or irreducible quadratic polynomials. And there are 4 cases that we will take a look at. We're going to let the rational function whose denominator d of x be given in proper fraction form. So the rational function is given in proper fraction form. So in the first case, we have the denominator is a product of linear factors with no repeats. And we will proceed by getting the factorization. 2x times x. We have our numerator 3x plus 1. And we know that 2, 5, and 12 do not have any common factors, which means that inside the first bracket, we cannot have a second number that is even. Otherwise, there would be a common factor of 2, which could be factored out, which means the common factor could have been factored out before breaking apart as 2 linear factors. So then we have some options of 4 and 3. I know the 4 cannot go inside. I can either get 4 times 3 or I can get 6 times 2. And I can't use 6 times 2 because they would both be even, which would pull out a common factor, which I do not have. So between the choice of 4 and 3, I'm going to put the odd number with the 2 and the 4 here, and it's just going to give me 8x and 3x, so I want positive 8x and minus 3x. So now, in order to decompose this, we have 3x plus 1 over 2x minus 3 times x plus 4. My only possibilities for decomposing are with 2 fractions, one with a denominator of 2x minus 3, and the other with a denominator of x plus 4. These fractions must be proper, which means that the degree of their numerators must be 0, and the numerators are constants. So I'm going to use capital A for the numerator of the first fraction, and capital B for the numerator of the second. Our goal then is to solve for A and B. We do that by getting a common denominator, and then we have to solve for 2 unknowns, which means we have to solve 2 equations. Well, once we have the common denominator, one fraction equal to a sum of 2 fractions, all with the same denominator, means their numerators must be the same. And so we will take a simplification. We could multiply both sides of the equation, if you prefer to think of it this way, by the LCD, which is going to cancel all the denominators, giving us an equation for the numerators. Now there are several approaches to solving this. One approach is to expand fully, and then notice that we have some constant terms and some variable terms. From here we can say that one equation comes from the coefficients of the linear terms, namely on the left 3 must be equal to a plus 2b. And the second equation must be that the constants on the right and on the left are equal. In other words, that 1 is equal to 4a minus 3b. And then we have a system of two equations we can solve by elimination or by substitution. However, another method or approach to solving is to recognize that I can substitute in different values for x, and the left side must be equivalent to the right side. And it might be easier to take a look at substituting in for x from the factored form. For instance, if I know that a is being multiplied by x plus 4, then when x is equal to negative 4, the a will be multiplied by 0. So if I take a look at x being equal to negative 4, I get an equation that says 3 times negative 4 plus 1 is negative 11, and that's equal to 0a. And then I have 2 times negative 4 is negative 8, minus 3 is negative 11, so I get minus 11b. And from here I get one equation with one variable, and I know that b is equal to 1. Now I can repeat the process by choosing the root of the second factor and substituting x equal to 3/2, which gives me that a second equation. Or I can simply take my value for b into one of the previous equations, 1 or 2 over here, and solve. But assuming that I started off with the red approach, I probably don't have these two blue equations. So then continuing on with x equal to 3/2, 3 times 3 over 2 is 9 over 2 plus 1, which is 11 over 2, equals 3 over 2 plus 8 over 2 is 11 over 2 times a plus 0b, and I get that a is equal to 1. And so now I know that f of x is equal to 1 for a over 2x minus 3 plus 1 for b over x plus 4. And you can do a number of things to check your answer. I'm just going to get common denominator. So from the menu, number, fraction tools, and then common denominator, I have 1 over 2x minus 3 plus 1 over x plus 4, and that confirms my original fraction. So from here I'm ready to do part B, which is the actual calculus. And I can integrate f of x as 1 over 2x minus 3 dx plus 1 over x plus 4 dx. And if we scroll to the very beginning of the lecture, in the first question of the warm-up, that's actually the one we had worked out and recognized the improper fraction form from the partial fraction decomposition. So we'll move on to the second case. Case 2 is when the denominator is a product of linear factors with some repeats. So we're first going to decompose f of x, which is x squared minus x. There is no need to factor the numerator, and I've already given you the denominator in factored form. But we notice that x plus 1 occurs twice. And so we are going to have a possibility of 2x minus 1, a possibility of x plus 1, and a possibility of x plus 1 all squared. And in this case, the numerators will all have constants. Now let's just talk about why this is. Why do we have both x plus 1 and x plus 1 squared? Well, let's consider the fraction 7 over 8, which is proper. And let's decompose it. We could say 6 over 8 plus 1 over 8. We could say 5 over 8 plus 2 over 8. We could say 4 over 8 plus 3 over 8. We could say 3 over 8 plus 4 over 8, but that's actually a repeat. 2 over 8 plus 5 over 8 is a repeat, and so would 1 over 8 plus 6 over 8. So we've got 3 different possibilities, and when we look at this, we notice that 6 over 8 is not reduced. So we have 3 over 4 plus 1 over 8. And we notice that 4 and 8 can be written in factored form as 2 squared and 2 cubed, respectively. 5 over 8 is reduced, so we can write that again as it is, but 2 over 8 is not. We can reduce to 1 over 4, and now we can rewrite the denominators in fully factored form, which would allow us to better get the common denominator, the lowest common denominator. 4 over 8 is not reduced, although 3 over 8 is reduced. And so we could rewrite this as 1 over 2 to the 1 plus 3 over 2 cubed. So the point of this exercise is to say that when we have a denominator that has repeated roots, or repeated factors, I should say, repeated factors, then within the partial fraction decomposition, any combination of their powers is a possible or legitimate denominator. For example, we have 2 to the 1, we have 2 squared, and we have 2 cubed. So we have to allow for a decomposition with all of those possible denominators. So similarly, that's what we're doing here. We're accounting for x plus 1 and x plus 1 all squared. So then we have to multiply each fraction by what is missing in the denominator. We have to do that for top and bottom. So the first fraction is going to be multiplied top and bottom by x plus 1 all squared. The second denominator is going to be multiplied by x plus 1 as well as 2x minus 1. I do like to give some space so that I can put these extra factors in nicely beside it. I should have spread it out a little bit more. And the third denominator is missing 2x minus 1. So we multiply top and bottom to unreduce. So therefore we have, if we were to multiply by the LCD, we have x squared minus x is equal to a times x plus 1 all squared plus b times x plus 1 times 2x minus 1 plus c times 2x minus 1. Now we could expand, get all of the quadratic coefficients together in one equation, all of the linear coefficients together in one equation, and all of the constants in an equation. We notice that we have plus 0 on the left-hand side. Or we could work smart by choosing some different values for x, namely the zeros of the factors, or the roots of the right-hand side factors. So I'm going to take x equal to negative 1, and this will give me equation 1. When x is negative 1, I get 1 minus negative 1, which is 2, equal to a times 0, plus b times 0 times doesn't matter what, plus c times 2 times negative 1 minus 1 is minus 3. So I get minus 3c. And so 2 is equal to negative 3c says that c is equal to negative 2/3. Then I'm going to choose x equal to 1/2. So when x is equal to 1/2, equation 2 tells me that 1/4 minus 1/2 is negative 1/4 equals a times 1/2 plus 1, which is 3 over 2, all squared is 9 over 4. So we get 9 over 4a plus b times 0 plus c times 0. And so if negative 1/4 is equal to 9 over 4a, that tells me that a is equal to negative 9. Now I don't have any other factors, and so I don't have any other smart choices for x. But we can choose any value for x that is easy to work with. And I think 0 is very easy to work with. So if we let x equal to 0, we can see that the left-hand side is equal to 0, and the right-hand side is going to be 1a. We're going to get 1 times negative 1, which will be negative 1b, or minus b, and we will get negative 1c, or minus c. And so since we know the values for a and c, we can solve for b. So b is equal to a minus c, which is going to be negative 9 plus 2/3, and therefore we get that b is equal to negative 27 plus 2, which is negative 25 all over 3. Now you do want to take your time and make sure you're doing this carefully. Before we go on and try to integrate, we should check our answers. For our purposes, we are going to use the graphing calculator to get common denominator with our 3 partial fractions. So, get common denominator, and our 3 partial fractions are a, which is negative 9, over 2x minus 1, b, which is negative 25/3, over the denominator of x plus 1. And then c, which is negative 2/3, over the denominator of x plus 1 quantity squared. And we've made a mistake. So we have to try it again. I'll leave you to find my mistake, and I'll come back and fix it. Once we have the correct partial fraction decomposition, you can go ahead and you can determine the integral of f of x dx by distributing the integral over each of the 3 individual partial fractions. So take a look, see if you can find my mistake. Maybe you found it already. I have a feeling I know where it is. Pause the video, correct it, and then check to see if the partial fraction decomposition adds up to give you the original f of x. Okay, when it came here, I had too much going on, and you should maybe write a little bit more, give yourself a little bit more space. And I had negative 1/4 equals 9/4 a. So negative 1 is equal to 9a, which means that a is equal to negative 1 over 9. Of course, that's going to affect my answer for b. And when I solve for b, I get negative 1/9 minus a negative is plus 2/3, which is 6 over 9. And so therefore b is equal to 5 over 9. So let's check on the TI Inspire and see if that makes a difference. So when we go through here, we had a was negative 1/9, negative 1 over 9. B is 5 over 9, and C is, let's do one thing at a time, positive 5 over 9, and C was okay. And so when we do this, we get the correct x squared minus x over the LCD that we had. Well, we assume it's the LCD. Maybe we should just try expanding 2x minus 1 times x plus 1 quantity squared, and we see that that is our denominator. Okay, so from here we would have the 3 individual fractions, which we can integrate using a method of substitution. Once you've done part B, check your answer on the TI Inspire. The third case talks about the denominator including irreducible quadratic factors with no repeats. So here notice we have x squared plus 1 and x squared plus 2. Thinking graphically about something like this, we have the basic parabola y equals x squared, and then we're vertically translating up one space. So all of the y coordinates are positive, and there are no real roots. As a result, we cannot further factor. We have a quadratic discriminant which is negative, and x squared plus 1 is as far as we can factor. X squared plus 2 is as far as we can factor that. So in order to decompose, we are going to have 2 denominators, 2 fractions, 1 for each denominator, rather 1 for each factor. But the difference is now we can have a linear numerator because we can have a proper fraction. So our linear numerator will have the form of ax plus b, and then the second one, cx plus d. So I've left a little room so that I can get a common denominator here. I recommend that you do the same. And now we have multiplying through by the LCD. Will give us x cubed minus 4x squared plus 2. And we can keep this in factored form, or we can expand it. In this case, we don't have any roots or zeros of the red factors, and therefore we will need to expand or come up with nice, easy values to evaluate, although none of the factors will become 0. So we can leave this in factored form, ax plus b times x squared plus 2 plus cx plus d times x squared plus 1. So we have a choice. We can either expand and get all of the common factors, all of the coefficients in individual equations, or we can choose different x values. The x values will not be so nice, but we can still try. You could use x equal to 0, 1, negative 1, and maybe positive 2. Or you can expand fully. I think I'll do that one just to show a different approach. So when we expand here, we get ax cubed plus 2ax plus bx squared plus 2b plus cx cubed plus cx plus dx squared plus d. And so we have 4 different unknowns, and therefore we need 4 different equations. And we can do that recognizing that there is no linear term, so we have a 0x in here. And so our cubic coefficient says that 1 must equal a plus c. And so that's equation 1. Our quadratic coefficient, or the coefficients for x squareds, tells us that negative 4, so this is equation number 2, negative 4 is equal to b plus d. We have linear coefficients giving us equation 3, which says that 0 is equal to 2a plus c. And the constant coefficients, or simply the constants, produce equation number 4, saying that 2 is equal to 2b plus d. And we have some nice symmetry. We have equations 1 and 3 are a system of 2 equations, and equations 2 and 4 form a system of 2 equations for 2 unknowns. So you can go ahead and solve the system, and then you can check by substituting a, b, c, and d into your partial fractions, getting a common denominator on the TI, and then going ahead and integrating the individual partial fractions. The fourth case is if the denominator includes irreducible quadratic factors with some repeats. So I'm going to have you pause the video and try to do exercise 4 on your own. Perform the partial fraction decomposition for f of x with the denominator factored as x times x minus 1 times x squared plus x plus 1, and then x squared plus 1 all cubed. Okay, pause the video and check with me. Okay, in this case we have f of x is going to decompose into 1, 2, 3, and then 4, 5, 6 different factors, different fractions. We don't have to go ahead and solve here. We're simply seeing how we would expand it if we understand the rules that we've discussed so far. Now I'm just going to check the quadratic discriminant for x squared plus x plus 1. I get 1 squared minus 4 times 1, which is negative 3, and therefore I have a quadratic expression which, as a function, would not cross the x-axis. Because we have a positive 1x squared, we know that the parabola is concave up, and the vertex must lie above the x-axis. Then I'm going to take my x squared plus 1, and since I've got cubed, I'm going to have 3 different denominators, recalling the 7/8 example that we saw numerically. And so each numerator has to have a degree 1 less than the denominator, and so we are going to get a constant, another constant, and a linear, and another linear, because even though this expands to be quartic, it still has a base which is quadratic. And again, the quadratic is the base, so we have ix plus j. And that would be applying all of the rules to this partial fraction decomposition. The remainder of the exercises then are asking you to apply the various rules, and we will go through a few of them to get started. Maybe you will complete these on your own. The first thing always to check when we are taking the integral of a rational function is to see if the rational function is proper. In this case, the degree of the top is the same as the degree of the bottom, so it is not proper. Now, we can perform long or synthetic division to find the quotient in the remainder. However, in this case, I'm going to take x minus 1 over x minus x plus 2 and rewrite it a little bit creatively. I can see that x minus 1 over x plus 2 is really x plus 2 minus 2 and then minus 1 again, all over x plus 2. And the reason I'm doing that is because I can group this together and I can divide x plus 2 into my two sort of factors here, or sort of terms. X plus 2 over x plus 2 is 1, and then we get negative 3 over x plus 2. So this integral will be the integral of 1 dx minus 3 times the integral of 1 over x plus 2 dx, which is going to give x minus 3 natural ln of the absolute value of x plus 2, and then plus c. In the next case, we have sine x cosine squared x all over 5 plus cosine squared x dx. And it doesn't look like a rational function in the sense that we have trigonometric functions, but we do have a denominator. And we have something repeated, namely the cosine squared x. We also have the derivative of cosine x, which is negative sine x. And so I'm going to try using a substitution to hide the details of cosine x. So I'm going to let t equal to cosine x, so that dt is equal to negative sine x dx. So making this change, I can rewrite this as negative the integral of cosine squared x is going to be t squared, and then the sine x dx has the negative dt, which I'll put separate here. And then in my denominator, I have 5 plus t squared, or t squared plus 5. And so I have a rational function now, and I notice it is improper, because the degree of the top is the same as the degree of the bottom. At least it is not less than the degree of the bottom. So I'm going to break this apart. Again, t squared plus 5 minus 5 can be what I rewrite the numerator as. And so I can do some regrouping in the top and get 1 minus 5 over t squared plus 5. And I still have the negative out front, so I'm actually going to make this negative integral of 1 minus 5 over t squared plus 5 dt. So I'm going to get negative the integral of dt plus 5 times the integral of 1 over t squared plus 5 dt. The first integral is easy to work out. The second one, we should be able to recognize it reminds us of a basic antiderivative. If we can't be reminded by the basic antiderivative, then we need to review the basic antiderivatives. What I'm going to do is get a 1 in this position, so I'm going to multiply the top and the bottom by 1/5, which is going to give me 1/5 over t squared over 5 plus 1. That 1/5 numerator will come out and join with the times 5. So far I have negative integral of dt, or negative t, plus 1 times the integral, so I won't use the plus 1. So I have plus dt over the integral of something squared plus 1. And in here I have t divided by square root of 5. So now I'm going to let m equal to t divided by square root of 5, so that dm multiplied by the square root of 5 is equal to dt. And from here you should be able to proceed, finish off, make sure you back substitute to t, and then back to x in your final answer. You can check back here for the solutions later on. In exercise 6, we want to integrate 1 over x squared minus a squared dx, where a is a positive constant. So we can factor x squared minus a squared, and therefore we can decompose the rational function. So it gets a little bit tricky working with so many parameters, and just be careful when you do so. So I keep saying I'm going to remember to bring this apart and leave some space for getting the common denominator. So I'm going to multiply the first fraction by 1 in the form of x minus a over x minus a, and unreduce the second fraction by multiplying by 1 in the form of x plus a over itself. And therefore we have that 1 is equal to capital A times x minus small a plus b times x plus small a. So I'm going to let x equal a, which says that 1 is equal to 0 times capital A plus 2 little a b. and therefore capital B is equal to 1 over 2 little a. And then I'm going to let x equal negative a, which says that 1, which is a constant independent of x, is going to equal negative 2 little a times capital A plus 0 times b. And therefore capital A is equal to negative 1 over 2 little a. So from here we can go back and substitute, and we can get that the original fraction, the original integral can be expressed as negative 1 over 2a times the integral of 1 over x plus a, and then plus 1 over 2a, as the constant can come out front, times the integral of dx over x minus a. Now you can do a substitution on each of these denominators, but because the coefficients are 1, it will not make a change of scale from dx to the new dm or dt. And as a result, we end up with negative 1 over 2a times the natural ln of absolute value of x plus a, plus 1 over 2a times natural ln of absolute value of x minus a, and then plus c. We notice that we have a common factor of 1 over 2a, and we also have the negative could come up top as an exponent here, which means that we can combine using the logarithm laws to say the ln of the absolute value of x minus a over x plus a, and then plus c. Of course, once you have an answer like this, you could let that be y, or f of x, and then working out y prime, you should be able to confirm your integrand function that you started off with in the integral, if we let y equal the answer. In part B, we have the integral of 1 over x squared plus 2x minus 3 dx, and we notice that the fraction is proper, so we are ready to factor the denominator and begin decomposing. And we have no repeats and linear factors, so we are going to have a over x minus 1 plus b over x plus 3. So we unreduce, which is the opposite of reducing, and we see that 1 is equal to a times x plus 3 plus b times x minus 1. So here we can let x equal negative 3, which tells us that 1 is equal to negative 4b, and therefore b is equal to negative 1/4. And we can let x equal to 1, so that 1 is equal to 4a plus 0b, and therefore a is equal to 1/4. And therefore the integral of 1 over x squared plus 2x minus 3 dx can be worked out as 1/4 the integral of dx over x minus 1 minus 1/4 the integral of dx over x plus 3. And we get 1/4 ln of absolute value of x minus 1 minus 1/4 ln of absolute value of x plus 3, and then plus a constant. And we can rewrite this as 1/4 times the ln of absolute value of x minus 1 over x plus 3 by our logarithmic properties, and then plus c. So you should make sure to be able to check your answers by applying derivatives to the final answer to confirm the integrand, the function that we were taking the integral of in the first place. Well, this concludes section 8.4, Integration by Partial Fractions. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.